The work that I'm going to present today is based on two recent NSF grants and is associated with these grants and lots of conversations and discussions with all these people that you see here, and they all have different backgrounds. Some are my students, some are my students' visitors, some are my computer science collaborators, mathematicians, engineers, even a statistician. So these two grants are service rates of codes. It's an NSF award for a very theoretical work, which I'm going to concentrate on today. And there is another one which is about redundancy for specifically storage in Edge Cloud. And it's a joint with proposal with BSF, and the PI there is Gala Yadgar, who is actually a computer scientist, systems person at the Technion. What I'm going to talk about today applies not only for Edge, but to a number of other distributed systems. So I have tried to remove as much math as possible, but at some point it really, to explain the point, I'll have to define certain things very rigorously. And in order for you to have something to do, if you get bored with that, here is a little puzzle, so which is related to this topic. So we have two movies in a city, and let's say that city has 200 people or 200 movie-going people, and there are two movies A and B, and 3 cinemas, and each cinema has 100 seats each. You can think about these seats as bandwidth. And lambda A people want to see movie A, and lambda B people want to see movie B, and we know that their sum is smaller than 200, but we don't know anything else about them. We don't know whether they will have, it may be that lambda A is 0 and lambda B is 200. So question number 1 is, which movie should each cinema play? So let's say your movies A and B are Aladdin and Beauty and the Beast, and you definitely should put one movie in one cinema and another in the other, but what should you put in the third one? And so one possibility is to XOR these two movies, and we are going to, this talk is about what this XORing or doing something a little more sophisticated will bring us with respect to how many people or which combinations of people can see what. Now, in order to get a movie B or movie A by say downloading movie B and movie A plus B, you would have to have 2 downloads, right? And in a movie scenario, you would have to pay for 2 tickets. So there is some cost associated with that. So here is the scenario, Aladdin, Beauty and the Beast, and an XOR. And the question number 2 is, if I do that, can lambda A people see A and lambda B people see B as long as their sum is smaller than 200? And the question number 3 is, can you describe all these combinations, all these possibilities for lambda A and lambda B that this redundancy system can support? Okay. So this is a puzzle, and now I'm going to formally define my system. So I have a distributed service model in which I have n nodes that provide service to multiple concurrent users. For example, Cloud Edge nodes can provide streaming, download, and they can also provide computing. So those A and B don't have to be, doesn't have to be content, it can be content which is associated with some computing, so description of a matrix with which you want to multiply, for example. And the node service depends on the data that node stores, in the sense that if you go to cinema 1, you only can see movie A. And we distinguish between 2 functional components at each node. One is associated with data storage, and the other is associated with service request processing. So let me first describe the storage. So a simple redundant storage is that you have k equal size data objects. In our movie example, we had 2, and they're stored across n nodes. In our movie example, we had 3 movies. And k is smaller than n, and hence redundancy. So for us, just think about objects as strings of bits. And all servers have the same storage capacity and to store one object each. And when I say, so what we can store on a node is either object itself or an XOR of two or more objects for now. General formulation would say that, that we can actually do something a little bit more complicated in terms of storage. And with such redundancy, a data object can be recovered from multiple sets of coded objects. So here is an example where I have objects A, B, and C, and then I have all possible XORs, A plus B, A plus C, B plus C, and XORing all three of them. And some coding theorists in the audience would recognize this as a simplex code, but just think about that as a bunch of XORs. And a way that you can recover A is by getting it from a server that stores that content by itself, or downloading B and A plus B and XORing them back to get an A. And you can continue with that. These sets are A1, 2 are what we call recovery groups for A, which we're going to define shortly. So now what about data service and request models? So different, let me just take care of something. Different practical service models are maybe mathematically equivalent, and we are going to consider two. One is a bandwidth model, and that's actually exactly like what we had in the cinema situation. You have a server which can accommodate simultaneously some mu downloads. And another is this one on the right, which is a queuing model where there is a server which processes its request for service at some rate mu. And what about requests? So requests for object I arrive at the rate lambda I, that's in the queuing model, but in the bandwidth model, the number of requests for object I, or number of requests for object I that are simultaneously in the system is lambda I. And so this is the only distinction that we are going to make here. And later they're going to be completely equivalent, and we'll not refer to these two models separately. Some people like to think in terms of the bandwidth model, some in terms of the queuing model, whatever it's easier for you, it's fine. So if I put this now together, I have this storage part, and then I also have this access part here where I have drawn queues. And so a request for object lambda A, I am allowed to split so that one part, lambda A1, is going to go to server A, and then another one is going to go through to this other, what we refer to as a recovery group, and it's called lambda A2, and so on. And this splitting, this collection, we are going to call request allocation for lambda A. So which request vectors lambda A, lambda B, lambda C can be serviced by a system is what we want to find out. And if you're thinking in terms of a queuing model, this would be a question: what is the stability region for this very complex queuing system? This is an optimization problem in general. And what I'm going to define is what we call the service rate capacity region. So set of that region consists of a set of vectors lambda 1 to lambda k that can be serviced by the system. And in our movie example, we had lambda A referred to people who want movie A, who want to see Aladdin, and lambda 2 or lambda B refer to the people who want to see Beauty and the Beast. And now we generalize this to lambda K. It's not only about content, I would like to remind you, but also that can be computing applications which are asking storage layer of the system to access certain data. And it can go even beyond the storage into computing. So again, lambda A is a request for object, lambda I is a request for object I, and a portion of it is assigned to a recovery set lambda ij. And so the requester vector lambda 1 to lambda k can be serviced by the system if it satisfies some constraints. And these constraints are, one is that no server is assigned the requests in excess of its service rate, right? Because many, for example, this movie theater that is showing XOR of A and B is of interest to B people and A people. So nevertheless, those A people and B people have to be fewer than 100 that the movie theater can host. So this is the no server is assigned the request in excess of its service rate. And the other one is simply that all requests are served. Some are served through direct seeing the movie A, right? And some are served by downloading components of these, downloading some content which will help you recover A. All right. So the problem, or there are several problems, and the formal formulation is as follows. K data objects are stored redundantly across n nodes. Data objects are represented as elements of some finite field. You can think about that as bits. Each server stores a linear combination of data objects, and requests for object I arrive at rate lambda I, and each node requests are serviced at some rate mu, that is 1. It's normalized. And here are some objectives, and today I'm going to talk about the first one, and that is determine the set of rates lambda 1 to lambda k that can be supported by the system that is implementing some common redundancy schemes. There are some other, and that is like, how do I design something that I want to support certain region? I know something about my moviegoers, right? And also, since many of these things, my knowledge is often stochastic, I may need to actually evaluate the performance of probabilistic systems. All right. So you may now ask, why is the service capacity region, or I will interchangeably be using capacity and rate region. Capacity is what we started with, but then very often we got some kind of information theoretic questions because people thought we are referring to information theoretic capacity. And so just saying rate region remove lots of headache about that, but capacity is much more often used in practice. Right? So what is the service capacity region? Why is it relevant to edge? Why is it an edge problem? So edge systems have unstable workloads and system state, right? And this is, we probably have heard and know more about that than even I do. And another is that there is no centralized resource management. So these are two main reasons. Nevertheless, they must provide the expected user perceived latency, right? So, and I would also like to provide a disclaimer and a claim that service capacity is not only of interest in edge computing, it actually, we believe it's an essential aspect of modern distributed systems. And someone just recently sent me this press release from Microsoft for a couple of weeks ago, last month, which says unlocking dramatic improvements to capacity management with Azure Quantum, which is actually saying that Microsoft now needs a quantum computer to solve some of these problems. Right? But these are much more complicated. I mean, maybe more nodes, more complicated problems that I'm going to present. Nevertheless, it's hard. So, so I was saying that requests are something that is uncertain in edge systems, meaning that there is lambda A and lambda B, and so like there are people who want to see Aladdin and people who want to see Beauty and the Beast, but we don't really know how many of these people in each category is going to be. But we may not only know that, this may be random numbers. So what I plotted here is a lambda A, which is a truncated Gaussian with mean 4 and variance 4, which is given, which is these blue dots, and lambda B is the red dots, which is 8 and 8. Sorry, blue dots is lambda A 4, and lambda B 8, and red dots is the opposite. And we don't know which one is going to happen. So we would like to be able to serve all of these. And of course, since it's stochastic and it's a truncated Gaussian, so there may be some requests, very unlikely, but very, very large numbers are showing up, that definitely we cannot do anything, but we can ask what we can do with some limited resources. And here I'm comparing several coding schemes, actually several redundancy schemes. Some are just about replication, and some are a little bit, the one which looks like a triangle is A, B, and A plus B. And then I'm asking what do they cover? And what I've assumed here is that two systems, one has only 3 servers and their capacity or bandwidth is 8. And the other has 4 servers and each has capacity 6. And therefore, they have identical cumulative service, so of 24. And here I've also computed, actually just integrated what how much coverage we get, and with this replication AAB and ABB, we only get about 70%, a little bit more. Whereas if we have a little bit more sophisticated code, we get 94, 95%. So that would be also have to be evaluated. All right, I think I'm going to skip some of the slides, and this is essentially telling you how to achieve this point, which is 15-0. So this what is the allocation for that? You have to be smart in deciding who to send where. And so for the last 5 minutes, I just would like to tell you that, and this here looks kind of combinatorial. So yes, there are 2 main techniques that we are using. One is combinatorial, another is geometric. And this combinatorial ones is starts with a classical coding theory where we define k times n generator matrix. And for our example here, we have this generator matrix just is vectors that are telling me how to XOR my data. So whenever I have data in the clear, like A, B, and C, I only have a single one. And whenever I have 2 data objects XORed, I have one in the corresponding places. So this last one, which XORs all 3, has 3 ones here. And some of you will recognize that this is again generator matrix of a 7-3 simplex code, which is a dual of a 7-4 Hamming code. So the recovery set is a subset of vectors. It has a little bit more formal definition, and this is something that we mentioned earlier. So recovery set for A is 2 vectors that when I XOR them, what I get is my original vector back. There is also, I can also associate geometry to this. And this here, funny looking triangle with these funny looking labels in the circle is, some of you will know it's the Fano plane. It's actually the most famous picture in discrete mathematics. And it corresponds to, again, the nodes here are what we call points in projective geometry, and they correspond to the vectors in this generator matrix. And this red line here is a line, actually, formally line. Why? Because when I XOR these 3, any line here, any connection between 3, when I XOR them, I get a 0. So that means that the third is a linear combination of the other 2, which means a formal abstract definition of line. I can also define something that we call the recovery graph of codes, and I will, in the interest of time, skip that. But it's a combinatorial object, which is kind of similar to this Fano plane, but it's only combinatorial. So matching on these graphs and geometry on this Fano graph are related. I actually realized how only in the process of writing this proposal. And both tell us something about the sums cumulative service rate that we can achieve. This I will skip. So what our work is about is, can we, for some particular graphs, some particular codes, find these combinatorial and geometric objects? We, of course, can do some brute force solution of the problem, what is it called? The optimization problem that I described, but that's not very instructive. Does not tell us what should we do if one of the servers dies, or how should we replace it, or if we have money to buy extra one, or how much someone else who joined this edge cloud community, say, can help us. There are a number of interesting problems in mathematics, but now, in order to allow at least a minute for a question, I just want to conclude and to say that this problem gets very technical, but it's actually answering the question, which data access rate can some particular redundant scheme support? And here there are 3 different storage schemes, a toy example, and the region of rates that corresponds to each of these schemes. And you can ask, of course, other questions. If someone gives you this region, how should your coding scheme look like? And that's something I'll talk a little bit about tomorrow. That's all I had to say. I guess I'll stop sharing now.